Okay, so we've just gone through the painful process of carrying out this convoluted experiment. What did we discover? What we have found is that by accounting for the fact, or the second postulate of special relativity, that light is always going to be a constant regardless of your reference frame, we found that the time elapsed by two events in different inertial reference frames are not the same. That time is going to flow in a different manner compared to observer A and observer B if they are in different inertial reference frames, okay? So we have identified that it's different, but we don't know how the effect transpires, how it comes into play, right? Does it differ by a lot? Does it differ by a little bit? Which one is running faster? Which one is running slower? So let's explore what we have just discovered and try and figure out if we can pinpoint the type of behavior that we're going to observe between these reference frames. So again, we found that delta t, or the time as observed by somebody in the S reference frame on Earth, is equal to this Lorentz factor gamma times delta t prime, or the time measured by the person in the moving reference frame, Terence. Now, what we want to do is we want to plot up this Lorentz factor here and see what kind of values we get, see how it behaves for different values of relative velocities, or this guy right here in the beta, and see what we can find. Okay, so if we do that, you could plop it in MATLAB, plop it in Mathematica, use Wolfram Alpha, use whatever you want to use. We get the following, okay? So we have this curve here. We see that gamma is pretty small, and it's pretty small for a lot of ranges of beta. Once we hit 0.5, I have tabulated values here. It's only 1.15 times the moving reference frame's time. That's not a big increase in time, but what we found here is that regardless of what value we have, gamma is always greater than 1, and it tends to go to infinity when beta gets large. So, initially, at these small ranges, below 0.8666, we're close to 1. There's not much of a change. And then above that, whoo, it blows up. Or we start getting these awesome effects coming into play here. And that's where it's bound by infinity. And what I'm going to say is that relativistic effects are most constrained to this region, to this range, or 0.866, which corresponds to a value of 2, as tabulated here, starts to blow up. When we get really close to the speed of light, 0.99995, or I'm going to say that again, 0.99995, the time difference is, we have a 100 factor here. So in this table, what we're finding is that time, or the Lorentz factor, is bounded between 1 and infinity. And it's always a positive value. So the time that is observed on Earth is always larger than the time as observed in the moving reference frame. That's what this equation is telling us, right? So the implied effect we just discovered, we're going to call it time dilation. As I say in physics a lot of the time, the names we give to concepts, the names we give to ideas, dictate the behavior of the phenomenon that's taking place. Dilation, think of dilation of your eyeballs. It means getting bigger, getting larger. So the time is getting bigger as observed by somebody on Earth, as observed by the stationary or observing entity. And it also means that a moving clock, the clock in the moving reference frame in the spaceship, is observed to move slow. It's observed to move slow. What do I mean by that? Let's observe that. So when this happens, let's say that Terence is going actually at 0.866 times the speed of light. So we get a beta of 0.866. And that's why beta is so useful, because we don't have to deal with C's. We just get this relative factor. Let's say it's going at that speed of light. And Terence says, hey, this took 10 minutes to happen. Of course, that wouldn't happen, but just for this circumstance to express what is going on in this relationship, he says, it takes 10 minutes for the light to go up and come down. My light was lazy in this situation. Philip, what do you get? He does this calculation. He's like, oh my God, that's why his face is so big. He says, well, this relation we just discovered, it says beta is 0.866. our gamma is going to be 2. If it took 10 minutes for you, you know what? It took 20 minutes for me. That's crazy. That's crazy. This seems so unconventional. It seems to take a slap in the face of our general wisdom, our general intuition, because this never happens quite often. Like, who disagrees about time? Hardly anybody. Hardly anybody. But the reason why this doesn't crop up in everyday events is because this guy is like flat. Look, it's flat. It has to do with the equation here. The gamma, the Lorentz factor, is about 1 until we go 0.5 times the speed of light. 0.5 times 3 times 10 to the 8th meters per second. That's 1.5 times 10 to the 8 meters per second. That's when we only get a relativistic factor of 1.155. So, in other words, in everyday situations, this is not observable. It does not arise. It's hidden beneath the layers, okay? And that's why I say here, when V is much less than C, beta is approximately 0, and gamma is about equal to 1, right? We don't get relativistic effects. That's why the Galilean transformation, when Philip and Terence did their experiment, that's why their observations, their time lined up. It wasn't different, right? Because this relativistic effect did not crop up. It only arises when we travel close to the speed of light. And that's why it feels so unintuitive. That's why it spits in the face of everything we know about the universe and physics, right? It's a very weird idea. And if it's hard to accept that time dilation is something that happens, just remember, this is a consequence of an observation we found, that the speed of light is constant, regardless of our reference frame, which we have tested again and again and again. Okay? So there's one other cool effect that's hidden in what we've just discovered. If we take this guy here, we know that if we divide by a number, we cannot divide by 0. So what's hidden in here? Well, we cannot divide by 0, and we also cannot have negative numbers under the square root. Right? So that means that if beta is greater than 1, we get a negative number, we get imaginary numbers, we get an imaginary time. We don't deal with imaginary numbers in physical quantities, right? Nature is nice. It behaves pretty well for the most part. So beta here cannot be less than 1. So what I'm saying and what I just ran through in my mind, I'll spell it out in terms of this. I say, 1 minus beta squared, this guy has to be greater than 0. So if you bring beta squared over there, take the square root, that doesn't change much. You get beta, or I'll make it match up for you guys. You get beta is less than 1. Okay, well, what does that tell us? Right here. Basically, this guy is less than 1. This guy is less than 1, which means that V is less than C, right? And this is why you've probably heard, maybe in sci-fi, maybe somewhere else, that the speed of light V, or not the speed of light, the speed of anything in the universe cannot exceed the speed of light. We see this with subatomic particles. We see this in CERN when they're doing their particle acceleration experiments. Nothing can exceed the speed of light. This is a cap on the limit of speed imposed by the universe. And it is 100% real. This is not fictional. This is a real effect that we observe. Okay? And time dilation, I want to make it clear, time dilation is an observable fact. Okay, this is something that you're going to see no matter what. It's going to arise. if you've seen the movie Interstellar, this is a different relativistic effect, but it's similar. You may remember that the individuals in the spaceship, they went down to that planet with heavy gravity, with those huge waves, and they came back up. They were, it's a different effect. It's more in terms of general relativity, which we won't get into, but the time had to bend to account for these ideas. Space-time bends to correct and account for the second postulate of special relativity. That's what's giving rise to all this stuff. That's what's giving rise to this. This is a real effect. It's something that's going to happen. I want to talk about one more thing, and then I'm going to talk about how we actually proved this. Different experiments we've done to show that, this weird, wacky idea is true, that it really happens. And what I want to say is that built into this experiment by design, there's a sort of an asymmetry at play here. And I did this on purpose. So you may have heard when I was explaining this experiment outlined right here that I want you to pay attention to the events that happen here. What I said is that in the moving reference frame, the two events, the flash of light and the detection of light, from which we're measuring time, they are synonymous. They happen in the same place. Two events are synonymous. However, in this reference frame, it doesn't have the same kind of symmetry. This guy and this guy, we need two people in different locations. The events have to take place at different spots. One is at x1, y1. The other one is at x2, y2. And x1 and x2 do not equal each other. This is different. This is different than this. And depending upon how you define these guys, your S prime and S, that's going to give rise to this effect. So, what you need to know is that the person who is moving always has a time that's lower than the observer seeing that moving thing. So, in other words, Terrence's time is always going to move slower. His clocks are going to move slower than Philip's and Eric's, the person stationary on Earth. As you can tell, that's sort of confusing. When you go through these kinds of problems, you don't have to keep track of what's S prime and what is S. What we say is that we're going to designate Terrence's time as a special time. A special time. We're going to call it what is known as proper time. Okay? And we're going to give it a designation, which you'll see in a lot of textbooks, as a naught. T naught. Okay? So I'm going to write this as such, T naught, and explain what I'm talking about a bit more. T naught, T naught. Okay, so this is proper time. Very important. Proper time, again, that is the time in the reference frame that is moving, or what is more important, it is the time as measured by somebody where the two events occur in the same place. Now, the reason why we call it proper time is because from somebody on Earth, from an everyday kind of situation, when you measure something, if you're in a car and you measure your trip, when you start the trip and when you end the trip, it occurs in the same place relative to your reference frame, right? You're in the car when it starts, and you're in the car when it ends. That's how we time things. Okay, that's how you time things. So it's proper in the sense that it gels up with our intuition, what we're used to viewing time as. So again, proper time is always selected as the time where the two events occur in the same place where they're synonymous. Okay? And what is going to happen is that time, as measured by somebody who is not moving, who is stationary, right? They're going to measure the two events. Their time is going to be dilated. It's going to be larger, which is documented in this equation here. Okay? So that inherent asymmetry is built into the problem. And now you're thinking, yes, I'm a master of special relativity. So I'm going to throw in something to mix it up a bit and really make you think about this. So I just talked about an asymmetry, but what I'm going to say, and it's going to sound sort of contradictory, so a lot of things will sound in special relativity. There is actually a symmetry at play in this problem. What? What am I talking about here? All right, so I told you there's an asymmetry in the sense that the two events occur at the same place in here, and they don't in this reference frame. But, you know, in this setup, Terence says, or rather, Philip says, Terence, your clock is running slow. That's just how it is. That's how it's going to be. But at the same time, we could have done this experiment in the reverse direction, which arises some symmetric property of the experiment, right? Terence could say, hey, screw this clock. You guys, you have the clock on Earth, and when I fly by, I'm gonna measure it. I'm gonna see what happens. So in that situation, if you have the clock on Earth, and this is sort of reversed, what's gonna happen is they're gonna measure the light coming up, and their picture, Philip's and Eric's picture, is going to look something like this. It's like what we would observe on Earth. If we shoot a laser up, it comes back down, and we don't have any sensibility about anything moving. But according to Terence and the first postulate of special relativity, we cannot determine that he is moving and they're not, or that they're moving and he's not. The first postulate of special relativity says that there is no absolute reference frame at rest. So because of that, and because we're in inertial reference frames, Terence is going to say, hey, I'm just standing here. You guys are moving. From his reference frame, looking out the window, it's going to look as though Philip and Eric are moving away from him. All right? He doesn't know that his ship is moving. He has no a priori knowledge. So it may look like these guys are the ones who are moving. And from his standpoint, what Terence is actually going to see, it's going to look like this same picture, but on Earth. Okay? So these guys are moving. And then what he will say is, according to S prime, we get something like this. The opposite effect. But if we account for proper time, the proper time is going to be the people on Earth where it goes up and down. And then Eric is just going to say it gets diluted. Right? It gets dilated. So we see here that there's an inherent contradiction, right? According to Terence, these guys are moving, but according to Philip, these guys are moving. Who's right, right? In this case, in the original case, when Terence is moving, Philip is going to say, your clock is running slow. And they're right. But in the reverse case we just discussed, when these guys are moving, Terence is going to say, wait a second, Philip, your clock is running slow. And he's right. Wait a second. Doesn't that contradict what's going on here? No, it doesn't. It works out. They're both right. This is special relativity. What you observe is relative. Right? Your perspective and the phenomena that arises is relative to your experience, to your reference frame. Okay, and that's what makes special relativity so weird. You should be like, what in the world is going on here? And we're going to take a look in the next video at something called the twin paradox, which resolves this for you and makes you feel much better, but they're both right. Philip thinks his clock is running slow, but at the same time, Terence thinks Philip's clock is running slow, and they're both right. Special relativity, folks. Weird stuff. All right. I'll resolve that in the next video. I can let you think about it. See if you can figure it out. What I want to do to wrap this video up is talk about how we proved all this stuff, right? We just discovered some really wacky stuff. We discovered that if you move close to the speed of light, the Lorentz factor is going to dilate time so that the proper time as observed by the individual who is synonymous with the two events, right? His time is going to be long. His time is going to be acting in a way that doesn't move as fast as the individual who is observing that when he's not moving. Okay? In other words, their time is going to be larger than the individual who is moving. All right? And this sounds weird. So whenever you discover something new in physics, you want to experimentally verify it. Now, at the time of this discovery in 1905, that was a monumental task. You cannot do that very easily, right? It was very difficult to take a clock and travel close to the speed of light and then compare the two differences. How do you do that? And in fact, we were not able to verify this, and everybody was like, whoa, that's crazy nonsense, until 1941. So in 1941, two individuals named Rossi and Hall, they were able to exploit the natural clocks of unstable subatomic particles. Okay, so subatomic particles, muons, so on and so forth, they tend to decay after a set amount of time, and we have this quantity known as half-life, which is the time at which half of the number of particles that are present decay, disappear, or vanish, whatever you want. And if you take these guys, you can use that as a very accurate clock. It's a very accurate, repeatable measurement. Okay? So what Rossi and Hall found, they said, hey, we got these muons. They're created in Earth's upper atmosphere, these muon particles. They're created when cosmic rays or energy come down from outer space, collide with our atmospheric particles, and you know what? They come down close to the speed of light, and they create these particles. So if we're moving close to the speed of light, if we measure the decay rate when they're at rest and compare it to those that are moving in, we should be able to pick up the time dilation effects. Okay? So we found that, by measuring at rest, the half-life, which I'm going to write as follows. The half-life, I don't have a lot of board space, but we'll make do. The half-life at rest, let me get my notes here, is 1.5 microseconds. Very short. Now, if we take the muons that are flying in, we're able to separate the different speeds and measure the decay rate, we should find that if we take this, the moving particle, the clock on the particle is moving. That's the moving reference frame. And it's also the reference frame for proper time, because the birth of that subatomic particle and the decay of the subatomic particle in the reference frame that's moving happens at the same spot. So according to us, we are this guy. We are not the proper time. So T1/2, we'll call that naught, is going to equal this, the gamma factor, times delta T 1/2, the proper time. Okay? So if this moves at 0.866, the speed of light, we get a factor of 2. We can do a very quick calculation. It should be 2 times 1.5 microseconds. You should measure something like 3 microseconds. Okay? Well, guess what? They did that measurement and they found, within experimental error, this was indeed true. I don't know what speeds they actually used, but I just use this as an example. So that was the first time we verified this weird, insane, crazy concept. All right? It's true. It's true. Our conception of the time was literally different. Our clocks flowed at a different rate. Okay? We observed that the muon clock flowed slower. All right? So, what other kinds of experiments were done to verify this? We've done a lot. The next one was done in 1971. We verified time dilation by taking very fast jet planes. In the United States Navy Observatory in Washington, D.C., we used atomic clocks, which are very accurate, very precise. And we flew a jet all the way around the world, came back to the Naval Observatory and measured the times. And what we found was that the time difference between the two was 273 plus or minus 7 nanoseconds. And compared to the theory predicted here by Einstein, time dilation, that predicted a time of 275 plus or minus 21 nanoseconds. This is within the tolerance of this guy, confirmed again. Now, what if I told you that basically every day you pop in a car, you do an experiment like this to verify time dilation? Because in fact, you are. What am I talking about? GPS. Do you use GPS? We used to have those TomToms, those big bulky devices. Now we use our smartphones. But what I want to tell you is that, yes, indeed, your GPS, global positioning system, which uses satellites and communicates from space down to Earth, we need precise measurements. So, that moving reference frame, when it's tracking our position, if we do not account for relativistic effects, we will be off. Our prediction of where something on the Earth, our global position, will be off significantly. In order to get good results, you must account for time dilation. So every time you hop in your car and you go take a trip, use GPS, you are verifying time dilation. You're doing an experiment that verifies this. This is a true fact. This is reality. So, yes, time dilation is weird, but it's true. It's something that happens every day. It's something that you verify every single day and use practically every single day. So what do we find? We found that time dilation arises as a result of accepting the second postulate of special relativity, that it does not matter what reference frame you measure light. Regardless of your reference frame, as long as it's an inertial reference frame, that speed of light will be constant. It's going to be c regardless of how you measure it, okay? It's always going to be c. So as a consequence of this fact, when you account for that, do some experiments, what we find is that time dilates, okay? The implied effect from it is known as time dilation, or that a moving clock is observed to move slow, okay? So using this, we developed this relation here. Delta t, the time where the events are not synonymous, is equal to this Lorentz factor times the proper time where the events are synonymous, and it gets dilated. All right, we get some weird effects. We're going to observe, or rather study this a bit more by taking a look at the twin paradox. Take a look at that symmetry I outlined, that weird event that both individuals think that the opposite thing is true, and they're both right in the next video. Hope you like it. Stay tuned.